Welcome to the interpretation of carbon-13 NMR. What that means is we're going to talk about how a structure, for example, carboxylic acid or an ester, how those carbons can be identified in the substance by using what is called NMR. Now, NMR stands for nuclear magnetic resonance, and the nuclear doesn't refer to radioactivity, but more as the nucleus of carbon-13. If you do remember, carbon-13 is unique because out of the three isotopes of carbon, carbon-12, carbon-13, carbon-14, carbon-13 has some magnetic properties, and so spinning electrons around the carbon give it a magnetic field that we don't see in the other two isotopes. At any rate, we're going to take some of the structures that we have here in the upcoming presentation and relate them to what we see on the spectrum. Now, this list of guidelines for carbon-13 are just guidelines for now, and they get more specific when you're in college level organic chem. But basically, the general idea is when you count all of these peaks, it tells you how many types of carbon there are. So we're not talking about just the number of carbons, but we're talking about the number of types of carbon. So that's going to be important to remember. And then again, there are times in a carbon structure when you have two carbons that are exactly the same. Those will only generate what we call one signal or one peak in the NMR. So we'll look at that also. And then carbons that are very similar will have separate peaks, but we'll see how sometimes we don't really need to know which is which. We just need to know that they will behave or produce a similar signal. So in line with what we talked about then, peaks that are near each other are representing carbons that are similar to each other. Okay? We'll talk about what is referred to as upfield and downfield. Those are concepts that are used not only in carbon NMR, but proton NMR. And then we'll talk about what is called a shift table and talk about how that helps us identify where carbons might be within a carbon structure. So let's take a look at this structure. This structure is an ester, and the reason it is an ester is because we have the C double bond O here, and we have the C single bond O here. So that makes it an ester. So what we have drawn here is a line that shows it should actually go from the carbon here to that place here. So here's what's happening. The oxygen here is electronegative, and it withdraws electron density from this carbon. In other words, electrons are drawn towards that oxygen, and it's also drawn towards this oxygen. What that means then is that this carbon is losing its magnetic field. Once it loses those electrons or that electron density, those electrons can't be spinning around producing a magnetic field. And because of that, the magnetic field of this specific carbon here in blue is much smaller. And so we see that it goes way down here in this region, around 170 and 180. And sometimes they can be even further down. Now the second carbon here, shown in green, is connected to that peak we see at about 60. And what that means is that this carbon, unlike the other one, only has a single bonded oxygen. And so this carbon is only losing electron density to that one oxygen. And so while it does lose some electron density, it doesn't lose as much. And so it maintains more of its magnetic field. Now here's how we phrase this. We would say that this peak is further downfield from this green peak here. Okay, so as you go left, away from zero, then you go downfield. So we could say that the green peak is upfield. Now you don't hear the phrase upfield as much, but nonetheless, everything to the left with higher numbers is referred to as going downfield. Now in this final arrangement, we have two arrows that go to the peaks here on the right. And they're there because they're not really affected by the oxygens and their electronegativity. Now, we have a decision to make here. The CH3 on the left is a methyl group, well insulated with the hydrogens. This carbon is well insulated by those hydrogens, as is this one. So why the preference? Why would this CH3 on the right be all the way over closest to 0, yet the other CH3 is upfield, or downfield rather, or further to the left? Well, this CH3 is in proximity with that oxygen, and so that oxygen, follow this now, that oxygen will withdraw electron density from the carbon, and that carbon becomes slightly more positive. And this carbon is also losing electron density to this oxygen. And because of that, this carbon is becoming slightly more positive. So this carbon on the end will start to lose a little bit of electron density. And we've said this before, if you lose your electron density, then you're going to lose your magnetic field. So that here is represented by the second peak. This carbon, this methyl group on the end, is well insulated, but it is far from these electronegative oxygens, so it doesn't really lose any electron density, so it's here. Now, what we refer to these methyl groups is aliphatic. It's really another way of saying something like alkanes or single bonded oxygen or single bonded carbons. So these are going to be upfield. Those that are near the oxygen are going to be further downfield. All right, so this structure here is a ketone. If you remember, there's a single carbonyl group here, and then R groups or carbons on either side. And once again, we see that carbon has that double bonded oxygen. It steals the electron density from this carbon. Once you lose electron density, then you lose your magnetic field. And so now this guy, way down here, near 200. So we'll see later on what is called a shifting table or a shift table, that's still acceptable, and it still describes a carbon with a double bonded oxygen. Now we can go to the right here and look at the CH3 group. We just saw this in the previous slide where this carbon surrounded by hydrogens is what we call insulated. But we have to remember too that this green carbon, if you can see it, is still influenced by this oxygen in the same proximity. So while it is further upfield, closer to 0, it's not below 20. So there is still some influence of that oxygen on the carbonyl group. Now we made a reference in the introduction that carbons that are similar to each other will in fact be placed similarly on the spectrum, and so that's what we see here. Now, what we're going to do in the next slide is talk about why is this, with a benzene group here, with 6 carbons, why do we see 4 peaks? But nonetheless, the fact that there's double bonds in here means that affects the electron density of each of the carbons in this structure. And so what happens is they are similar, but they're closer to this carbonyl group here far on the left. So when we have a benzene ring, we're going to find out that each of those carbons, in fact, does lose electron density. And because of that, it loses its magnetic force, and so it's going to be further downfield from 0. Let's look more specifically now at this situation of the benzene ring. That carbon A, we've drawn these 4 lines across this benzene, and this carbon A here is only one of a kind. And so it is unique, and so that's going to get a separate peak on the carbon NMR. But if you look here, these 2 carbons on these points right after that are actually identical. They're both CH, right? They both have a double bond attached to them. So while these 3 inside alternating double bonds make it look like they're not the same, they actually are. You have to remember in resonance that these double bonds are alternating. So while we draw it here, in these positions, then they alternate. In other words, that resonance structure is actually a variety of versions here. So let's just suffice to say that B, carbons B, at these 2 junctures are actually identical. That happens again with C. Now, here's how it works. Carbons that are labeled as B are actually the same proximity away from this carbonyl group, or from this A, but they don't have the same, they don't feel the same impact as C, because those carbons here are just further away. And that's all we need to be different enough to get a separate signal on the carbon NMR. And finally, D is furthest from the carbonyl group, and it is different from carbon A. If you think about carbon A, is a single carbon, but it doesn't have any hydrogens attached. Carbon D here is a single carbon, but it does have a single hydrogen attached. So that's one of the ways we distinguish to make sure that we know that there are 4 types of carbon in this benzene ring, but there's a total of 6. Now this is one of the more straightforward examples for you, except we have one added feature here. The carbon that is attached to the oxygen, right, that carbonyl group here, that is designated way over here, downfield past 200. We've talked about that before. There are 2 CH3 groups here on the end, 2 methyl groups here, well insulated. So that's going to put us down closer to 0. Okay, but they still are influenced by that carbonyl group. And then there's this interesting little peak here. It's thicker than the other ones. What that is a signal for the solvent. So when we test acetone, we have to put it in some chemical that causes it to dissolve. But a chemical that dissolves acetone will also have carbon in it. So this peak usually occurs at 77. And we don't count it as any of the numbers of carbon. So if you remember, this peak here, far past 200, and this peak here, closer to 0, that tells us we have 2 types of carbon. But if we look at the structure, we see that we have a total of 3 carbons. Okay? So now we have this 77, which doesn't count as either one of them. So be careful. Don't see this as 3 peaks or 3 types of carbon, but really 2 types of carbon and 1 representing the solvent. Now, sometimes they don't show the solvent, and sometimes they do. Just look for that 77. This should be a fairly straightforward example, and it's a great example of how you have 1 peak, but that you have 6 carbons here. The one thing I would point out is that because of the double bonds, remember those double bonds are alternating. Okay, so they're not just here as shown, but through resonance, they're also where we see single bonds. So that resonates, it goes back and forth. Well, because of those, this peak here isn't closer to 0 like you might expect for a carbon with hydrogens all around it. That double bond does have an effect on its magnetic field, and so that's why it's a little bit further to the left. And again, here's that peak at 77. Just another example here. You see the methyl group here, CH3, well insulated with hydrogens. That's going to be easier to see here, and that puts us below 20. Okay, so in the previous example, we saw that the peak for a carbon was just above 20. But now we see this CH2 here, insulated with hydrogens, but because of its proximity to this oxygen, it's going to be further downfield. Okay? And then finally we see that 77 again, and that represents our solvent. This is just another example how a carbon that is further away from the oxygen will be closer to the 0, because now we have a carbon that is closer to 10. And this first peak here, at about 12, is actually representing this methyl group on the end of the propanol. And then this second peak here represents this carbon that is 1 carbon closer to the oxygen. And now we have this carbon that's closest to the oxygen is actually represented by this peak here at about 60 or something like that. And then again you see the solvent represented at 77. This is a good NMR example for you to look at because it numbers the carbons and so it relates to the peaks, but we should walk through that just to make sure here. We'll start with C4, which is just below 15. Okay. This group here, carbon 4, is a methyl group, well insulated, far away from that oxygen. This is actually a duplicate of one of the first slides that we looked at. At any rate, these hydrogens insulate that carbon's magnetic field. And so it is placed here closer to 0. This similar CH3, okay, because it's in proximity to carbon 2, which is near this oxygen, this carbon 1 is affected by that oxygen. And so it's going to be a little bit further downfield. Okay, we don't have to talk about every single thing here, but again, there's the C2 representing this carbonyl group. Here's an interesting thing here. This CdCl3, this carbon trichloride, for example, or carbon methyl trichloride or something like that. Just one of the solvents here at 77. This is a good example to go back through to make sure you understand. This is what we call a shift table. Now let's talk about the term shift. What we talked about previously is that carbon 13 has a magnetic field associated with it. We know that. Okay. But what's happening is that we imagine that there's a magnetic field that is applied to a substance. And so what we've talked about is, one of the ways to remember is that what if we had a large magnet off to the right of this spectrum here? It's an imaginary magnet, it's not a real magnet, but we imagine that there's this large magnet here. Carbons here near 0 represent those carbons that have strong magnetic fields. We could imagine that they are strong, and so they can withstand being near a big, strong external field. If we go way to the left, we talk about carbons that have a very weakened magnetic field, like carboxylic acids. Those carbons are losing their electron density to a double bonded oxygen. Okay, so what we could say is that those carbons with really weak magnetic fields would have to be far away from this magnetic field we might imagine here on the right. Okay, so it's just a way of remembering. But let's look at what these shift tables. Oh, by the way, the shift comes from the idea that once we turn off the magnetic field, the carbon 13s return to their original direction. And when they do that, they give off energy that we can read. And so that's called a shift. It shifted from where the magnetic field placed it, and it shifts back to where it was after the magnetic field is turned off. Okay, let's take a look at some of these structures here between 0 and 50. Now, we have a carbon with a chlorine, a carbon with a bromine attached. Okay, those are not so common in the work that we're going to do, but this is certainly important. Saturated alkanes. Alkanes are single bonded carbon hydrogens, and alkane is also a reference to CH groups. Saturated means it's full of hydrogen, so these carbons have lots of hydrogen, and that's kind of what we were talking about with insulated, okay, or shielded. That's another term that you'll hear. So these carbons are shielded by the hydrogen here. Okay, this is reference to an amine, for example, or an ammonia group, or a nitrogen rather. We don't see those too often in what we're doing. This is an aromatic. AR stands for aromatic, and those are those benzene rings that we saw. So carbons that are attached to the aromatic would be down here. We're not talking about the carbons that are within an aromatic. We'll see those later. But all of these red carbons here, right, just pay attention to what they're attached to, because that's really what's going on here. So this here represents a ketone. But the carbon that we're talking about is the kind that's attached to the carbon with the double bond, not the carbon directly attached to that oxygen. Okay, sulfoxides and sulfones we'll deal with in college level organic chem. Triple bonds we're not going to see too much of. As we go further to the left here, now we can talk about carbons that are within the aromatic or within the benzene ring. So that's what's going on here, is carbons that we find within a benzene ring have a whole range. If you see, they go from about 95 all the way to about 160. Okay, so we would see that peaks that fall within this range, they would be possible aromatics or heteroaromatics. In other words, things that are that have aromatics, but things that are attached to them also. Here we see carbons with double bonds. Far to the left, we see those characteristic C double bond O. Now, don't be fooled. This carbon here is actually attached to that oxygen. Okay, you have to remember, an aldehyde has a carbon double bond oxygen. But the way they drew it here, if we put the H on the oxygen, then we would think it's an alcohol, and that's not what we want to do here. So aldehydes and ketones both have double bonded oxygens, So they're far down here to 200, but you'll see that there's a range for the ketones, and it goes between 100 and, let's say 190 all the way to 210. Same thing for the aldehydes, okay? Down here you'll also find carbons that are in carboxylic acids, esters, and amides. And finally, this is just another version of a shift table. Like periodic tables, they have a variety of versions here. And so you'll see that, again, aldehydes and ketones are far to the left, and the chlorine and iodine and halide bonds are down here. Alkanes, they don't designate this as saturated, but that's a general idea. So that's a general idea of how carbon NMR relates to structure.